Hello, this is Sareem from Exam Help Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 PP2 Variant 1, May June 2018. Question number 1, Part A, state what is meant by a scalar quantity and by a vector quantity. So a scalar quantity has only magnitude, while a vector quantity has both magnitude and direction. Part B, complete figure 1.1 to indicate whether each of the quantities is a vector or a scalar. So power is a scalar quantity, temperature as well is a scalar quantity, but momentum is a vector quantity since it involves velocity. Part C, an aircraft is traveling in wind. Figure 1.2 shows the velocities for the aircraft in still air and for the wind. The velocity of the aircraft in still air is 95 meters per second to the west. The velocity of the wind is 28 meters per second from 65 degrees south of east. Part 1, on figure 1.2, draw an arrow labeled R in the direction of the resultant velocity of the aircraft. So a resultant velocity would be this way. Part 2, determine the magnitude of the resultant velocity of the aircraft. So this is the velocity with which this aircraft is traveling, which is 95 meters per second. The wind has a speed of 28 meters per second and is at 65 degrees to south of east. The resultant is going to be this length by using cos theta formula, which is resultant is equals to root of the sides square, 95 square plus 28 square, minus 2 multiplied by 95 into 28 into cos theta, which is 65 degrees. And so we have the magnitude of resultant velocity as 110 meters per second. Question number 2, part A, state Newton's first law of motion. So this is an object remains at rest or keeps moving with a constant speed until a resultant force acts on it. Part B, a block of weight 15 newtons hangs by a wire from a remotely controlled aircraft as shown in figure 2.1. The aircraft is used to move the block only in a vertical direction. So this block moves either upwards or downwards. The force on the block due to air resistance is negligible. The variation with time of the vertical velocity of the block is shown in figure 2.2. The velocity is taken to be positive in the upward direction. Okay, so figure 2.2 suggests that the block rises in air with speed of 0 meters per second and reaches the highest or the maximum speed of 3.4 meters per second, and then it changes its direction by crossing the x-axis, and then it comes to the negative side of the y-axis. This means that it has changed its direction and now it's moving downwards with speed 0 meters per second and reaching a maximum speed of 6.8 meters per second with a time interval of 2 seconds. Now part 1, determine for the block the displacement from time t is equals to 0 to t is equals to 3 seconds. Okay, so for displacement, we first need to calculate the distance it covers when it rises up in air and when it travels downwards. When it rises up in air, which is this part of the graph, the distance it travels when it travels upwards is going to be the area under this graph, which is half into base, that's of 1 second, into height is of 3.4 meters per second. So half into 1 into 3.4, which is 1.7 meters, and then the distance it travels when it moves downwards, which is this part of the graph, area under the graph, which is half into base, which is of 2 seconds, and height is of 6.8 meters per second. So half into 2 into 6.8 which is 6.8 meters. So now we know that it travels 1.7 meters upwards and then it travels 6.8 meters downwards. The displacement is the shortest route from the starting point until the finishing point, which is this part of the distance. So magnitude of displacement is going to be the difference between this distance and this distance. So 6.8 minus 1.7, the displacement it covers is of what, 5.1 meters. And the direction of displacement, it moves 6.8 meters downwards and 1.7 meters upwards. So direction of displacement is going to be vertically downwards. The change in gravitational potential energy from t is equals to 0 to t is equals to 3 seconds. So it moves 1.7 meters upwards and then it moves 6.8 meters downwards. The change in height is 6.8 minus 1.7, that's 5.1 meters. So change in gravitational potential energy is going to be mass into 9.81 into this change of height. So mass into 9.81, which is equals to 15 newtons of the weight of the block. So 15 into change in height, which is of 5.1 meters. And so the change in gravitational potential energy was of 77 joules. Part 2, calculate the magnitude of the acceleration of the block at time t is equals to 2 seconds. So by looking at figure 2.2, you can deduce that the graph is a straight line, which means that from t is equals to 0 until t is equals to 3 seconds, there is a constant acceleration throughout. So we can take any two values from the graph and the time interval for that change of velocity. So let's suppose I'll take the final velocity as 3.4 meters per second and initial velocity as 0, and the time interval for this change of velocity is of 1 second. So 3.4 minus 0 divided by 1, and hence we have the acceleration as 3.4 meters per second square. Part 3, use your answer in B. Part 2 to show that the tension in the wire at time t is equals to 2 seconds is 20 newtons. So the formula is resultant force is equals to mass into acceleration. The two forces acting on the block are the tension of the wire and the block's weight. So tension minus the block's weight, which is 15 newtons, is equals to mass of the block, which is 15 divided by 9.81, and the acceleration at time t is equals to 2 seconds from the previous part is 3.4 meters per second square, and hence we have tension as 20.2, which is also equals to 20 newtons when we round it to two significant figures. Part 4, the wire has a cross-sectional area of 2.8 into 10 to the power of negative 5 meters square and is made from metal of Young modulus 1.7 into 10 to the power of 11 pascals. The wire obeys Hooke's law. Calculate the strain of the wire at time t is equals to 2 seconds. So Young modulus is equals to stress over strain. Now stress at t is equals to 2 seconds is going to be force divided by area. Since we are dealing with strain of the wire, we are going to have tension in the wire as the force. So tension of wire is 20 newtons divided by area of the wire. The cross-sectional area of the wire is 2.8 into 10 to the power of negative 5. And that's 7.14 into 10 to the power of 5 pascals of stress. So strain is going to be equal to stress over Young modulus. Stress is of 7.14 into 10 to the power of 5 pascals. And the Young modulus of this wire is 1.7 into 10 to the power of 11. And that's how we get a strain of 4.2 into 10 to the power of negative 6 with no units. Part 5, at some time after t is equals to 3 seconds, the tension in the wire has a constant value of 15 newtons. State and explain whether it is possible to deduce that the block is moving vertically after t is equals to 3 seconds. Okay, so after t is equals to 3 seconds, tension and weight would be equal, and they are acting in opposite directions. So the block starts to move with a constant velocity or comes to a rest position, and it gets into an equilibrium state. So we can write that block comes into equilibrium state because now tension in the wire which acts upwards is equal to the weight of the block, and they both are 15 newtons and are in opposite directions to each other. So block comes into equilibrium, block is at rest, or is moving with constant velocity. Question number 3, part A, state what is meant by the mass of a body. So that's quantity of matter in that body. Part B, the two blocks travel directly towards each other along a horizontal frictionless surface. The blocks collide as illustrated in figure 3.1. Block A has mass 3m and block B has mass m. Before the collision, block A moves to the right with speed 0.4 meters per second and block B moves to the left with speed 0.25 meters per second. After the collision, block A moves to the right with speed 0.2 meters per second and block B moves to the right with speed v. Part 1 used Newton's third law to explain why during the collision, the change in momentum of block A is equal and opposite to the change in momentum of block B. So Newton's third law discusses how force on both objects will be equal in magnitude but opposite in direction. So we're going to write about how during the collision force on both the masses 3m and m, is going to be equal but in opposite directions, and hence we're going to have the same rate of change of momentum since force is equals to rate of change of momentum, and the time interval for which they are both in contact with each other is going to be equal for both bodies. So we can write that force by 3m block A is equal to force on block B but in opposite direction. Force is equal to rate of change of momentum and time interval for which both are in contact is equal for both bodies, block A and block B. Part 2 determines speed v. So following the law of momentum, which is momentum before collision is going to be equal to total momentum after collision. Total momentum before collision is going to be this mass multiplied by this velocity plus this mass multiplied by this velocity. But remember, velocity is a vector quantity, so we must take negative sign into account with 0.25 since this block is moving towards the left. So 3m into 0.4 plus m into negative 0.25. This is going to be equal to total momentum after collision, which is 3m into 0.2 plus m into v. So 3m into 0.2 plus m into v. This is equals to 1.2 m minus 0.25 m, 0.6 m plus mv. All the m's get cancelled, and hence v is equals to 0.35 meters per second. Part 3, calculate for the blocks the relative speed of approach. So this is the sum of the speed with which they are approaching with each other. So 0.4 and 0.25. That's a 0.6 meters per second. The relative speed of separation, so we'll subtract the velocities. So v is 0.35 and the final velocity of 3m is 0.2, so we'll subtract them. And that's 0.15 meters per second. Part 4, use your answers in B. Part 3 to state and explain whether the collision is elastic or inelastic. So for a collision to be elastic, its relative speed of separation is supposed to be equal to its relative speed of approach. Since in this part of the question they're not equal to each other, this means that the collision is inelastic. I can write that relative speed of approach is not equal to relative speed of separation. Thus, the collision is inelastic. Question number 4, part A. For a progressive wave, state what is meant by the period. So period is time taken for one oscillation, one complete oscillation. The wavelength, it's the distance between two adjacent wavefronts. Part B, figure 4.1 shows the variation with time of the displacement of two progressive waves P and Q passing the same point. The speed of the waves is 20 centimeters per second. Calculate the wavelength of the waves. So wavelength is equals to speed divided by frequency, where frequency is 1 by time period. So frequency is 1 by time period. We first need to find the time period for wave P and Q and confirm if they have the same time periods. Now, time period for wave P is going to be from 0.15 seconds until 0.75 seconds. So this time interval is the time period of wave P, which is 0.6 seconds. Now the time period for wave Q is from 0.05 seconds until 0.65 seconds. So time period for wave Q is also equals to 0.6 seconds. Now that we have the time period, we can find the frequency, which is going to be equal to 1.67 Hertz, and hence wavelength is equals to 20 centimeters per second divided by 1.67, and the wavelength we get is of 12 centimeters. Part 2, determine the phase difference between the two waves. So phase difference is going to be the time delay between these phase shifts, the time delay between these. So this is 0.15 and this is equals to 0.35. So 0.35 and 0.15, the time delay is of 0.2 seconds. Now you need to divide 0.2 by the time period of the wave, which is 0.6, and multiply that by 360 degrees to get the phase difference between the two waves. So phase difference would be of 120 degrees. Part 3, calculate the ratio intensity of wave Q by intensity of wave P. So intensity is directly proportional to amplitude square. Instead of intensity, we can take amplitude of wave Q and P and then square them to get the ratio. Amplitude is the maximum displacement. So amplitude of wave Q is 3 and that of P is 2 millimeters. So we have 2 square divided by 3 square, and the ratio we get is of 0.44. Part 42, waves superpose as they pass the same point. Use figure 4.1 to determine the resultant displacement at time t is equals to 0.45 seconds. This means that the resultant displacement will be the sum of displacements of both waves Q and P at t is equals to 0.45 seconds. Now displacement of wave Q at t is equals to 0.45 seconds, which is this on the x-axis. This is the displacement of wave Q at t is equals to 0.45 seconds is equals to 1 millimeter, and that of wave P is negative 3 millimeters. Now the sum of negative 3 and plus 1 is negative 2 millimeters. So the resultant displacement is going to be of negative 2 millimeters. Question number 5, part A. When monochromatic light is incident normally on a diffraction grating, the emergent light waves have been diffracted and are coherent. Explain what is meant by diffracted waves. So in right, that waves spread at slit. Coherent waves are waves with constant phase difference. Part B, light consisting of only two wavelengths is incident normally on a diffraction grating. The third order diffraction maximum of the light of wavelength and the fourth order diffraction maximum of the light of wavelength are at the same angle theta to the direction of the incident light. Part 1, show that the ratio second wavelength divided by the first wavelength is 0.75. So the formula for diffraction grating is that wavelength is equals to d sine theta divided by n, whereas n is the number of the order diffraction maximum forming. Lambda 1 d sine theta divided by n, which is the third order maximum for lambda 1, so n has a value of 3. And then for lambda 2, we have d sine theta divided by 4, since lambda 2 forms the fourth order diffraction maximum of the light. Now they're asking us to find the ratio of lambda 2 by lambda 1, and they share the same angles, and of course they share the same d value as well. So d sine theta divided by 4 and divided by d sine theta divided by 3. So when you take the reciprocal of it, d sine theta and d sine theta, they get cancelled and it becomes 3 by 4, which is equals to 0.75. Part 2, the difference between the two wavelengths is 170 nanometers. Determine the wavelength lambda 1. So let's suppose that lambda 1 is of x nanometers. So lambda 2 would be of x minus 170 nanometers. Now they have already given us the ratio of lambda 2 by lambda 1. So x minus 170 divided by x is 0.75. And so we have lambda 1, which is also x, equal to 680 nanometers. Question number 6, part A, define the volt. So this is joule per coulomb. B, a battery of electromotive force 4.5 volts and negligible internal resistance is connected to two filament lamps P and Q and a resistor R as shown in figure 6.1. The current in lamp P is 0.15 amperes. Part 1, use figure 6.2 to determine the current in the battery. Explain your working. Okay, so when current across P is 0.15 amperes, the voltage across P is equal to 2.7 volts, and since they are in parallel connection with each other, they share the same voltages. This means that at 2.7 volts, Q has a current of 0.09 amperes, and the current divides in parallel connections. So sum of 0.09 and 0.15, which is 0.24 amperes, is the total current in the battery. So 0.09 and 0.15. This is equals to 0.24 amperes. Part 2, calculate the resistance of resistor R. So they're asking us to find the resistance value of this resistor R, and now we know that the total current flowing across this battery is 0.24 amperes, and 0.15 out of 0.24 flows across lamp P, and the remaining will flow across lamp Q. And when current across P is 0.15 amperes, voltage across P and Q is going to be of 2.7 volts, meaning 2.7 volts across P and 2.7 volts across Q as well. This also means that V across R would be 4.5 minus 2.7, since this parallel connection of P and Q is in series with the resistor R. So 4.5 minus 2.7, which is 1.8 volts. So this is the voltage across resistor R, and the current across it is 0.24 amperes. Now we can get the value of resistor R. So R is equals to 1.8 volts divided by 0.24 amperes of current, and hence the resistance of resistor R is 7.5 ohms. Part 3, the filament wire of the two lamps are made from material with the same resistivity at their operating temperature in the circuit. The diameter of the wire of lamp P is twice the diameter of the wire of lamp Q. Determine the ratio length of filament wire of lamp P divided by length of filament wire of lamp Q. So length of the wire is directly proportional to the resistance of that wire. So resistance of lamp P is, when it has a voltage of 2.7 volts across it, it has it has a current of 0.15 amperes flowing across it, and hence at that point of time it has a resistance of 18 ohms. And now resistance of lamp Q is going to be equal to, when it has a voltage of 2.7 volts, it has a current of 0.09 amperes flowing across it, and at that point of time lamp Q has a resistance of 30 ohms. Now when area doubles, length increases by 4 times and resistance too will increase by 4 times. So length of filament wire of lamp P, which is directly proportional to their resistances, so 18 divided by 30, 18 will be multiplied by 4 because lamp P will have its resistance increased by 4 times, so it will have a ratio of 2.4. Part 4. The filament wire of lamp Q breaks and stops conducting. State and explain qualitatively the effect on the resistance of lamp P. So when lamp Q stops working, current across lamp P will increase, and it would now be exactly equal to the current flowing across the battery, which is 0.24 amperes. As a result, voltage across R will decrease, and when increased PT flows across lamp P, according to figure 6.2, when voltage across lamp P increases, resistance of lamp P will increase too. So we can write that voltage across R decreases, current across P increases, thus resistance of lamp P increases. Suppose if the lamps were obeying Ohm's law, according to the formula, resistance is equals to voltage divided by current, when current is inversely proportional to resistance. If the current had increased, the resistance would have decreased. But since over here they are a non-ohmic conductor, these two lamps, they are not going to obey Ohm's law, and hence the relationship would be different this time between resistance and current. A beta minus particle from a radioactive source is traveling in a vacuum with kinetic energy 460 electron volts. The particle enters a uniform electric field at a right angle and follows the path shown in figure 7.1. Part A, the direction of the electric field is in the plane of the paper. On figure 7.1, draw an arrow to show the direction of the electric field. So beta minus particle is deviating upwards, which means this negative particle is being attracted to this side of the this square, which means that this side is positively charged while this side of the region is negatively charged. Electric field lines, they start from the positively charged side and end at negatively charged side. So we will be having vertically downwards electric field. It's supposed to be a straight line. Part B, calculate the speed of the beta minus particle before it enters the electric field. So the kinetic energy with which this beta minus particle is approaching this electric field strength of area, it is of 460 electron volts. Now we need to convert that to joules. Each electron volt is equal to 1.6 into 10 to the power of negative 19 joules. So 460 electron volts would be 460 into 1.6 into 10 to the power of negative 19 of joules. This is going to be equal to half into mass of beta minus particle is exactly the same as the mass of an electron. So this is 9.11 into 10 to the power of negative 31 into v square. And so the speed of the beta minus particle with which it is approaching that electric field region is 1.27 into 10 to the power of 7 meters per second. Part C, other beta minus particles from the same radioactive source traveled outside the electric field along the same incident path as that shown in figure 7.1. State and explain whether those beta minus particles will all follow the same path inside the electric field. So we can write that beta minus particles travel with a variety of speeds, and when there is a change in speed, the deviation with which it moves towards the positively charged plate will be different. So it travels with variety of speeds, and so they all take different paths. So that was the end of the paper. Thank you for watching.